Okay, the next model is the case where we relax the assumption that we have instantaneous receipt. So that is, when you place an order at the conclusion of the lead time, we assume that the entire order will be shipped in one single lot. And we will get it at the end of the lead time. But we are relaxing that, so which means your order will be shipped to you gradually, okay, over a period of time. And this is typically the case when you have a production situation, whether you have a lot that is being produced and the lot will be produced over a time. So it's going to you're going to have inventory coming into stock over a period of time. For this reason, it's often called production run model. Instead of economic order quantity, we use the term production for this model. But this will work even for vendor orders if the vendor ships the order quantity or gradually over a period of time. So what happens here is then, instead of the inventory jumping up to Q in one instant, instead it rises gradually over a period of time over which the quantity ordered is taken into stock. So once the order quantity is completed, then there is no increase anymore in inventory, and then the inventory will start declining at the rate of demand. The demand being constant, then it's going to go down gradually to zero. Okay. Once again, we can calculate what the lead time demand will be, and we can place the order sufficiently ahead of time so the shipment will begin right at the time when our on-hand inventory reaches zero. So now this is our inventory cycle. One cycle will last that long, so it will have a period, and we'll call this production period. That is when the inventory will be taken into stock. So we will have a production phase and then no production phase. Okay, so the demand is going to be there all the time. So what is the rate at which the inventory will rise? Okay, so now during the production period, inventory is coming in at the rate of, let's say, P. P is your production rate, lowercase p. Okay, and then let's say lowercase d is our demand rate. So inventory will be coming in at the rate of P, and it will be going out at the rate of D. So P minus D is the rate at which the on-hand inventory will rise. Okay, and of course the decline will be at the rate of demand D. So with that being said, P minus D, then we can tell what this maximum will be. We know that the maximum is not going to be the value Q like in the EOQ, because in EOQ it's instantaneous, so the entire order quantity becomes the maximum inventory. But the maximum inventory here is going to be whatever that point is. Then once we figure out that point, then we can say that the average inventory will be that maximum divided by 2, and not Q over divided by 2, because in this phase of the inventory cycle, we start with 0, we end with I sub max, the maximum inventory level. So 0 plus I sub max divided by 2 will give you I sub max over 2 as the average inventory in this cycle. The same happens here in reverse. So you start with I sub max and you end with 0. So I sub max plus 0 divided by 2 will be the average inventory in this phase of the inventory cycle. So for the entire inventory cycle, I sub max divided by 2 is the average inventory, and that would be the case for one cycle after the next. So with these notations, Q being the order quantity, now C sub S is, we use, instead of C sub O, we use C sub S as setup cost, because we use the production metaphor here. So production, we don't have ordering cost, but we have setup cost. So C sub S, and then holding cost is the same as before, and we use lowercase p for production rate and lowercase d for demand rate. So they both must be in the same time unit, okay, the week or month or whatever. And then T, let's say, that is the length of production run. Okay, so now we have to figure out what will be the maximum inventory level. So we know that the inventory will rise at the rate of P minus D, and if we can figure out how long it will rise, then we can multiply by that time period, and that will be our maximum inventory. P minus D is the rate at which inventory will rise per day, say for example per day or per week, whatever the case may be, per time unit, right? So if we can figure out how long the production run will be in that same time unit, then we can multiply by T and we will get the value for I sub max. So that turns out to be Q over P. Q is the production quantity and P is the rate at which we are producing. So Q divided by P will give us how long the production will last. So T is Q over P. All right. So then, well, maximum inventory level, actually this is easier to visualize in this way, and which is same as that. So it so happens so that will be the maximum inventory, which is the same thing as that. Okay. So Q over P, if you take here, if you take Q over P out, then you get Q over P times P minus T. So that will be the maximum inventory, and that divided by 2, so that divided by 2 will give you the annual holding cost. Instead of Q over 2 times C sub H, you'll have I sub max over 2 times C sub H. That will give you the holding cost. Your setup cost is same as before, so it is D over Q times C sub S. So instead of C sub O, we use C sub S just to as a caution. So this is not the EOQ formula. This is the POQ, production run model. Then once again, like in the EOQ, the minimum cost occurs when these two costs are equal. So we set one cost equal to the other and juggle a little bit, and we get this formula. So this is our optimum production quantity formula, OPQ.